Welcome everyone to this workshop. So today we're going to have a look at building domain-specific clip models with an in-depth look at actually training and implementing OpenAI Clip. So I'm James. I'm the staff developer advocate over at Pinecone. If you're unfamiliar with Pinecone, we're a vector database that makes it super easy to build vector search application. So just before I introduce Federico, I want to just say a couple of things very quickly. If you miss anything, we are going to record this presentation, so you'll be able to find everything over on our YouTube channel, on Pinecone YouTube channel after this, and we will also send you an email with a link to that afterwards as well, so you can share that wherever. If you do have any questions, put those in the Q&A box. I know the chat isn't working right now. I'll try and get that fixed as soon as possible. So without anything further, I will pass over to Federico, who's a postdoctoral researcher at Stanford NLP Lab. So go ahead, go for it.
Yeah, sure. Let me share my screen. Okay, so thanks a lot for inviting me. So today we talk about domain-specific multimodal machine learning with Clip. And the general idea is that I'll go over what is Clip and how it is trained, and I'll show you a specific use case on which we fine-tune Clip on, that is a fashion use case. And I'll show you a bit of the things we've been working on, how we somehow implemented those. I have some code on Colab that I'm gonna show you a bit to explore some details somehow of the implementation, and then I go also over a demo we have on Streamlit. One thing to say that is that like everything I'm gonna show is open source, or is gonna be open source as soon as like we get communication of the destiny of our paper, and also like the dataset we're going to use. Farfetch, that is the company we've been working with, is going to release it. So soon everything that's explained in this presentation will be open source. So hi everyone, I'm as James said, I'm a postdoctoral researcher at Stanford NLP. I'm working mainly on NLP and multimodal methods. I did a couple of different things during my previous research years. I have like some public GitHub project on topic modeling. I was also part of the team that trained the Clip in Italian. I work on Reckless, that is like kind of like a black box tool to evaluate recommender system. So if you are ever interested about like this topic, feel free to send me an email and get in touch. So what we'll talk about today is Clip, an application of multimodal models to fashion. What I'll be talking about today is the results of a collaboration between different people. Patrick, Jacopo, and Ciro are the ones that have like the Chibi logo, so are the one for which I show the Chibi logo. But there are also like other people like Silvia, Anna, Giuseppe, and Diogo that are part of different university and different institutions that allowed us to somehow this collaboration between companies and university allowed us to bring what is Fashion Clip to life. So let me go directly into the question we want to answer. So we know that like recent research, at least in the last couple of years, have collected a lot of good results for text model. We know we have BERT, we have GPT, and the last decade was the decade of like good image models, so ImageNet and models trained on ImageNet that can classify a lot of things, and more recently the vision transformers. The question we want to try to answer now is that can we use somehow model that combine language and vision for domain-specific use cases? So most of the data we have is actually unstructured. If you think of, for example, of catalogs in the fashion domains, you don't often have annotation. You have images, for example, the dress, and a caption that describes the dress. Is there a way, the question is, to bring these two words together so that we have a model that can use this information at the best and provide a way to build a general classifier over a different kind of task? And the answer is yes. What I'm going to talk about is a subset of the things that have been done in the last couple of years. I'll talk about CLIP, that stands for Contrastive Language Image Pre-training. And CLIP was introduced 1.5 years ago. And in the last year, there have been a lot of improvements over CLIP, but the general idea in CLIP is still fundamental in all the models, and that's what I'm gonna talk about. I have in the slides some recent literature. I'll share the slide after the talk. So like if people are interested in looking at like more recent development of like language and video models like Blip, for example, or Flava or GroupVit by NVIDIA, I think this could be like a very high level sum up of what has happened in the last year for vision and language models. So CLIP, that is the main component we are going to talk about, is this big model that connects text and images. What CLIP does essentially is to bring images and text in the same vector space in a way that we can compute the similarities between an image and a description of the image. CLIP has been trained on 400 million examples. So it's like it has been trained on data from the web. And this already should like give an indication of the idea behind CLIP. So it's to somehow apply a distance supervision paradigm in which we don't need annotation. We just collect, for example, data from the web, and we train a model that should be able to generally encode text and images. The idea in CLIP is as follows. If we have an image, this is the image of like 2 people on the mountain, and this is the description, what we would like to have is that we can somehow move the image in a vector space. This is a 2D vector space, but you can generalize this to n dimension. And we also want the description of 2 people on the mountain to somehow be close to these in the vector space. And this is the general idea of how CLIP is designed. What you need to build CLIP, and this is like the basis for all somehow recent visual language model, is an image encoder that gets the image passed through a deep neural network that can be CNNs or vision transformers, and gets you a vector in a chosen dimensionality. And you also need a text encoder. So starting from 2 people on the mountain, you have a text encoder that could be BERT or LSTMs for principle, and you get a vector out of this. So you have 2 somehow towers. Each one is gonna output a vector for the modality of interest. Which data do you need to train CLIP? Is batches of images and captions. So you need, for example, let's assume we have a batches of size, in this case, 2, 4, if we consider all the elements. We have the image of 2 people during sunset and the image of 2 people on the mountain. These are the description, for example, 2 people during sunset and 2 people on the mountain. So we have an image and the matching caption, another image and the matching caption. And we can look at the images and the caption in this way. So we can somehow create a table that is going to be our similarity matrix, in which we want to somehow learn that the matching caption for this image is 2 people during sunset, and the matching caption for this image is 2 people on the mountain. So we have like this diagonal kind of representation in which we want to eye similarity. So these two should match, but this element should be 0 because the caption 2 people on the mountain does not describe this image. And this is going to be our somehow target representation matrix. So how do you actually train CLIP? Well, this is now the idea of the contrastive blobs is pretty simple, and it's like super easy to implement. If you can think about it, it's just like once you have the text and image encoder, it's going to be like super easy to implement this, because we start from the text, 2 people during sunset, 2 people on the mountain. We pass this through the text encoder, and we generate vector representation of 2 people during sunset and 2 people on the mountain. So these are 2 embedded representation, or 2 vectors representing T1 and T2. We do the same thing for the images. So we pass the images to an image encoder, and out of the image encoder, we get image 1 and image 2. So vector representation for the 2 images. What we can now do is that we know that we have this target representation. So we know that image 1 should match with target 1, with text 1. what we do is that we compute the dot product, or the somehow in this case is similarity because these embeddings are normalized, but this is the idea of the similarity between the image 1 and text 1, image 2 and text 1, image 1, text 2, image 2, text 2. And the idea is that we want this to be closer to 1 and this to be closer to 0, so as to somehow represent this idea of matching the caption with the respective image. So what happens during training is that we have this similarity matrix, and we want to make this similarity matrix more similar to this target representation, and we can do this with standard categorical cross entropy loss. And what will happen is that this similarity will go up, this similarity will go up, this will go down, and this will go down. So the general idea is that we are going to use information in the batches to learn to represent images and text. What happens somehow underneath the training is the following. Think of like having like this image that is 2 people on the mountain, the description of 2 people on the mountain, and the image of 2 people during sunset. What happens here is that the training is going to move the red dot far away from the other 2. So this is what is going to happen. And the general idea is that after training, we will have a representation that puts the image of 2 people on the mountain close to the caption, 2 people on the mountain, and the somehow unrelated image will be far away from this kind of situation. And this is done by obviously training on the similarity, as we saw in the previous slide. And this is somehow a self-supervised. It's not like super self-supervised because you still need the caption, but it might be like somehow referred to as distantly supervised because data is being collected from the web, and training just requires collecting this data and just run it through this pipeline. So once you have a vision encoder and a text encoder, that could be like, if you use Hugging Face, you could take Hugging Face for the birth from Hugging Face and the vision transformer from Hugging Face. You just need to generate a vector representation on each of the 2 tower and just train this similarity matrix to represent these embeddings. So what happens after training is that obviously what you pull out from CLIP is the encoder. So you have an image, you generate a vector, and you have a text encoder, and you generate a vector. So you generate vector representation, and if the training was successful, it should be that, for example, this image and this caption in the vector space are similar. So they can be compared, you can compute the similarities, and you can use it for many different possible tasks. Now, talking about task, what do we need CLIP for? Why we go through this kind of pipeline to generate this model? And the idea is that we can use this for example, zero-shot classification. Once we know to embed images and caption, it's super easy to actually learn to actually classify things, because we have the image of a cat and we embed it with the somehow image encoder. We have the labels a cat, a dog, and a boat in the sea, and we're going to embed this with the text encoder. And again, if the training is successful, the label a cat that describes this image is going to be close to the image of a cat. And so this eventually is doing classification and just looking at the nearest neighbor of the label with respect to the image embeddings. And this is, I think, one of like the main properties of CLIP is that it allows you to do zero-shot classification on many datasets without training on the actual dataset. So it generalizes confidently well. We'll see that like in some cases, for example, in the fashion domain, as we apply this, it's better to fine-tuning if you want to get better results. But the general idea is this one. You can do zero-shot classification just by looking at the similarities between images and labels. Another thing you can do is language image retrieval. So that is somehow the same kind of task as the zero-shot classification, but swapped. So we start from the description 2 people on the mountain. We have a vector space. We embed all the elements. And eventually what we're going to see that 2 people on the mountain is going to be closer to this image than this image. And this is somehow the effect we would expect to see. So model has never been trained on this task. The model has been trained just to put together in the vector space captions and images, but it can somehow learn to do this kind of task through this kind of proxy training. So we can do both zero-shot classification and language image retrieval just through this kind of distantly or self-supervised training. So as long as you have images and caption, you don't need other data to train a CLIP model. You need a lot of data to train CLIP. So people at OpenAI use 400 million images. Other models recently show that you can lower this number a bit to 12 million images. That is still a lot of data. One thing you can instead do is that you can fine tune the model, and that is like using the recent kind of model that have been released. It's very easy. There are scripts to fine tune this on Hugging Face, but also like on the original OpenAI's kind of GitHub. But it is that you just need somehow data to do this, and CLIP has been trained to do one thing, but can do actually many more. Like it can be used in many different ways. So quick summary of OpenAI's CLIP. CLIP generalized very well on different data sets. It reached an accuracy on ImageNet of, I think, 0.70%, if I remember correctly. And that means that CLIP does this in a zero-shot manner, so without seeing one example of ImageNet. And these are just some example of the classification you can do with CLIP. But again, this shows how useful CLIP can be in many use cases in which you have a data set of images, you want to label it, but you somehow getting annotator is too costly for you. CLIP is also very useful in other kind of tasks. This is just an example of image generation in which CLIP is used as somehow a guiding element to generate images, but also like the recent Stable Diffusion use a CLIP large, if I remember well, to actually learn to generate images. So there are a lot of things that you can do once you have like a general purpose model like CLIP. Now let's get into somehow the main part of our talk today. So the idea is that we wanted to create a domain-specific multimodal model for a fashion use case, and the work is currently under review, but I'm going to show you most of the things we did, and we will play a little bit with this. But first of all, I have like a couple of slides of like what you can look at if you want to fine tune your CLIP. So there are a couple of different scripts that I think are, or like somehow repository that I think are relevant. The first one is the original OpenAI's code that allows you to load the PyTorch model, and then you can fine tune it yourself. You just need to define the PyTorch data loader, load, caption, and your images, and you can just like backpropagate starting from the model they propose. There is also the Hugging Face contrastive language image training scripts, and these are the ones that have been used to train CLIP Italian. These are like very simple, and they somehow are more representative of, it's not a family of model, but of like what is usually called hybrid CLIP, that is not starting from CLIP, but using a already trained image encoder, for example, Google Vision Transformer, and already trained text encoder, for example, BERT, to train an embedding model that puts image and text together in the vector space. And this is generally referred to as somehow hybrid models, I guess. And the last one is OpenCLIP. That is a very nice project that has been done to replicate CLIP training on openly available, publicly available dataset. For example, the Lion dataset. There is the entire training code that replicate the training process of the original OpenAI CLIP. And the good thing about this is that all these are very easy to use. So you just actually need your data, and you just need to change a couple of lines of code to actually fine tune your CLIP model. There are a couple of things you might want to keep in mind. For example, having a large batch size is very important in CLIP. So you might need to get good GPUs, and you need at least a good amount of data to actually fine tune this. What we used in Fashion CLIP is 1 million, almost 1 million fashion images, but still, I think like you can fine tune it pretty easily, and it doesn't cost much, as we'll see later. It doesn't cost much to like take the original CLIP and fine tune it on your actual data set. So what do you need as a summary is good quality data. So this is essential to get good result. And I think it's the most important part of most machine learning processes. The code is there. You can fine tune easily with Clip, but also with more recent models, but you need to have good quality data. So good images and good captions, definitely. So now let's get into the more fashion clip part. The question was, can we build a clip-like model for fashion? So fashion has somehow a more specific language than general language, and we want to our language and vision model to be able to somehow support this. So we need a somehow model that can be trained on fashion data with low supervision, and that can be applied to different downstream tasks. So you can think of, for example, if you train fashion clip, you might have a new client with a new catalog of images. What you can do is that you can pre-annotate all the images from the catalog using a zero-shot model. So you can predict if the image is of a shoe, a red shoe, or I don't know, a shirt or a dress, whatever. You can pre-annotate the data, reducing the effort from the annotation team to actually go over all the images and annotate them by hand to then put them into your website. And then the idea is that the fashion clip is also an interesting kind of look for research in our somehow point of view. The idea is that it is a domain-specific representation of language in which we can probe the model for language understanding in a way that is not super easy to do with Clip that has been trained on tons of data and for which there might be a lot of like confounding variable when we evaluate the model itself. So Fashion Clip has been brought by a couple of different people from different university and different institutions. Farfetch allow us to use 800,000 fashion products with image and text pair. And thanks to them, we have been able like to train this fashion clip that is clip fashion aware somehow. And the idea of having fashion clip is that since fashion clip is not trained on at level of classification, it can actually be used on a lot of use cases. And as I said before, you can pre-annotate the data. And for example, you can classify product for styles. For example, you can predict if something is an elegant kind of shoes or it's more of a sporty shoes. And this scale up manual labor by a lot. So it scale up like the merchandiser work by a lot. But also there is another kind of contribution, that is the fact that since Fashion Clip has not been trained on a domain on a specific brand, it should be able to generalize to a lot of different data sets. So it's not been trained on a specific brand. Fashion Clip has been trained over the entire catalog of a big retailer like Farfetch. So it should be able to do some kind of out-of-the-box context understanding, can be used for search, can be used for classification in many different ways. So what the data set that like the people at Farfetch gave us was of 800,000 image with description and metadata, and we worked somehow to build a good caption. And this is another thing that is very important. So if you have metadata, it's important to use the metadata to build the caption. And eventually what we came out with is caption of this kind of type, in which we swapped some elements to make the model more resilient to kind of noise. But the idea is that this is a green polo with a modern kind of style. And we train the model with this kind of caption. So for training, we just use the original OpenAI model, and we fine-tune the entire model. So both the image encoder and the text encoder on our data set, and we tend to use a low learning rate to avoid catastrophic forgetting in the model. So we use these and we train the model. So the question now is our implementation of Fashion Clip better than Clip? So the idea is that we trained a model on fashion data, but it is better than the original Clip. This is somehow a very important question, because it can happen that when you fine-tune Clip, you might overfit on the data. So you have a model that does not generalize, or worse, you end up having catastrophic forgetting, and the model forgets a lot of what it has learned during the original training, and that makes it like not as useful as it could be. So we tested these on zero-shot classification task. The image is just to remind you of how the task is somehow done. So we have the image of the cat, a cat, a dog, and a boat in the sea. We put all together in the vector space, and we look at the similarities. With Fashion Clip, this is essentially the same. So we have an image and the labels. We generate the embeddings for both. So we generate the embedding of the image with Fashion Clip, and we compute the similarities between the embedding of the image and the labels. And what we expect is that the image is more similar to the label dress, since this is an actual dress. We use a couple of different data sets in the literature, Fashion Mist, the Kaggle dataset, and Deep Fashion. And we do classification on the categories. So we try to predict the actual category of an item. And we also use our own in-domain dataset. So like the category scheme given by Farfetch. What we can see is that like Fashion Clip works much better, like several points in F1 with respect to the normal clip on this dataset. And this suggested like in this particular use case, fine-tuning clip on your data is an effective way to get a better model that you can use to do zero-shot classification on unseen data. So Kaggle, FMNIST, and Deep are completely unseen by the model, and it showed that like the model can generalize to kind of this new data. The other task is like, this is not zero shot, this should be like image retrieval, is again getting the caption and finding the corresponding image in the dataset. And the scheme is mostly the same as the one before. So we have a red dress, we generate the embeddings, we embed all the images, and we find the image that is most similar to the caption a red dress, hoping to find this kind of image, for example. And again, the result, these are mainly on our Farfetch dataset, show that the model can actually learn retrieval much better than Clip. So on our test set, it performs much, much better. Then we had like some out of category. So what we did was kind of like a dataset ablation in which we removed a category on the dataset that was, I think, sportswear, and we remove all sportswear from the dataset, and then we used Clip, the fine-tuned Clip, to somehow classify sportswear, and it worked better than Clip. But also we tested by removing brands, so we removed 2 brands from the dataset, we fine-tuned the model, and then we compare the performance in zero-shot brand classification on in zero-shot category classification on zero-shot retrieval, and we actually saw that Fashion Clip performed better even if it hadn't access to that data over any kind of similar data over training. So that suggests again that like Fashion Clip generalize and it works well on retrieval. But we'll see some of these, I guess, in the demo I have ready for you. So summary of Fashion Clip. So the first result is like Fashion Clip beats Clip in several fashion-related benchmarks, also on held out dataset, but also on like out of distribution fashion data. But the cool thing is that like training Fashion Clip is relatively cheap. Training this clip for a couple of epochs costed $31. And you have like, there are more details in the paper, but the general idea is that it doesn't cost much to fine-tune Clip on your domain-specific dataset, and the improvement is actually a lot. This is just fine-tuning. Obviously, training Clip from scratch requires much more time, but if you just need to fine-tuning, doing this is actually easy and effective to do. So now, what can we do with Fashion Clip? So we know that it works well, but are there like some kind of thing we can do that are fun to play with Fashion Clip? And the answer is obviously yes. One very cool thing is that it works super well for product search. So when we search, for example, for t-shirt with a cat, what we find is actually like an image of a t-shirt with an actual cat. And this does not happen when we do like text search on the search engine. So it brings a huge improvement on the search engine, because it actually learned to map specific properties of object to the vector space. Look at, for example, light red dress, in which it actually finds a light red dress, but this don't happen for text only search that has no content understanding of what light red means. So the good thing is that Clip learns somehow to, let me use the word, understand this kind of concept, and helps you to find this representation in the vector space. Another thing is actually product search. So we've built this demo app that I'm gonna show you in a bit, but it is that you can search for different objects and find interesting object in the vector space. This is like, for example, striped shorts, and it should indeed find striped short. Like I said, everything is open source. This web app will be open source soon as we get back from the people that manage the dataset, but you can already see why these can be useful for like a domain-specific application, for example, search on a search engine website. Another very interesting thing is that we can study the relation between language and images, and this is more interesting, I think, under a point of view of research, but it's also cool that we can explore the space and better understand what the model is looking at. So one thing that, like Rafael, that was invited, I think, a couple of weeks ago to speak here at Pinecone, was this occlusion algorithm for linguistic localization. The idea is that we want to understand what the model is looking at when we input the query a cat. So for example, if we have the image of a cat, we generate a vector representation. We have the query a cat, we generate the vector representation. And if we compute the similarity between the image and the text, we get, for example, 0.8. What happens if we start to put black patches on the cat? It happens that the similarity drops. So the more we cover the cat, the more the similarity drops. For example, this is a bit higher because we can see more cat, and this the similarity is at the lowest because we cannot see the cat. With this process, what we can actually do is that we can actually learn where the cat is by looking at what happens when we put black patches on the image. So when the similarity drops, when there is a black patches, it means that the algorithm has found something. So in this case, since the similarity is very low, behind the black patch, there is a cat. And this, for example, can be like a couple of examples. For example, if we search for the word cat here, what the model will do by combining different patches is that it's going to highlight it behind here, whereas actually a cat. And obviously, we can do the very same kind of thing with dog. So same image, we search for the word dog, and the model is going to highlight this part that is actually the face of the dog itself. So now some example of like the linguistic capabilities of Fashion Clip. And the idea is that it can perform obviously language image retrieval. This is a shirt with a tiger on it, where the caption has never mentioned tiger. So the model learned this from the actual training process and generalizes across different kind of concepts. But the interesting thing is that we can explore the space, and we also can classify the space by looking at how Clip recognize concept. For example, this is an image of a polo, and when we search for short sleeves, the model is going to highlight this part. When we have the image of like this jumper, it happens that if we search for long sleeves, the model is going to highlight this part and these parts that are the actual long sleeves. In this example, we search for the word bag, and the model actually highlights this part. And if instead we search for the word jacket, the model is going to highlight another part. So the model actually, with this process, we can probe the model for like understanding of fashion-specific terms and see if the model learns actually to recognize where things are in the image itself. This is, for example, the recognition of a logo. And this is the same logo, but smaller on an image. And again, you can see that the model is able to recognize where the logo is and detect it in the image. And this is how the model is probably able also to classify stuff, because this can be used also to classify along the brand axis of the data set. Another important thing, I guess, to look at is the generalization of this model. So the entire thing we have been explaining here rests on the idea that Fashion Clip generates good representation for images and captions. And we wanted to a bit open somehow this fashion clip model to better understand what's behind it and what can be used to do domain-specific multimodal machine learning. A first example is the figure on the right, in which there is the plot of like clothing concept by embedding images between fashion clip and clip. There's the silhouette score is not reported here, but it's higher for fashion clip. So fashion clip generates better, for example, image embeddings than clip, and it clusters together things that are similar so that it can somehow be used to do this kind of like computational representations. The idea is that we are able to ground somehow content, and this is what makes somehow fashion clip very useful, because as we saw before, we can recognize different objects. For example, we can recognize where is the ankle strap, where is the actual sandal, where is the actual high heel of the object, and this is what we can use to actually probe content in our representations. Another thing we did to better understand the generalization is to test fashion clip on things that do not exist, that we call improbable products. And this comes more from like how somehow children learn that they generalize to new concept very quickly. And the question is, can this model generalize to new fashion concept very quickly? So for example, the idea was to generate novel products. For example, this is a product that does not exist, that is a Nike cocktail dress, a black Nike cocktail dress. And the idea is that we want the model to, we want to see if the model is able to effectively predict that this is a Nike long dress with respect to other kind of destructure caption. So again, this dress does not exist. We have these labels, some of which are obviously the structures. And when we tested the model on a bunch of different products, we saw that like the model effectively is able to detect the correct somehow description. And in this context is Nike dress. So the model somehow has this kind of ability to ground the language and to deal with the language composition to some extent. This does not work in all cases, but it's nice to see that to some extent this model is able to capture some kind of like linguistic compositionality that is eventually what we would expect to get from our somehow deep language model or deep visional language models. Just to show this is what happens when we do the search of the brand and we find the actual brand image. Another thing we did was like to see if we can apply this in another context. For example, there are sometimes you want to find you find for example a nice t-shirt, but you want to get it darker, or you want it, for example, longer. So can you somehow walk through the space to find items that are similar to the original items, but that have just one attribute that has changed somehow in somehow a representation? And what you want to do is that you want to move in the space by keeping many attributes fixed, but you want to move along the axis of one relevant attribute. For example, you have a shirt and you want to get it like of another color without changing the shirt itself. The idea is that what we saw is that like fashion clip, but in general also clips, encode geometric properties of the space in which we can actually explore the space and we can actually better understand the representation and the relationship between different images, but we can also search in the space for things that are darker or things that are longer by just moving along the axis of the space. So what we do behind this is that in general, we move across the axis of one of the attributes and try to find similar things. But what you see here is that, for example, from women high heels, we want to find women flats, so more flat kind of things, but we want to keep somehow the style consistent. This is, for example, the changing color of a polo, going from being dark blue to more light blue. This is somehow a zero-shot recommender we implemented. The paper describes everything more in detail, but it's somehow a cool application of what your fine-tuned model can do easily on novel data. So I almost reached the last part of this part of the talk. I want to mention a couple of things that I think are super important to mention. First of all, clip is like I said, not the somehow latest model in literature. Is definitely one of the most somehow important one if you want to use this word. But the idea is that there are novel, innovative kind of additional losses that you can add to the contrastive loss. And I suggest to look at Blip. That is a very interesting model that reached very strong performance on a couple of different tasks. Training code is online, and again, you just need your data and to start training this model. But there are, like, in the first couple of slides, there was a list of like the recent literature that I suggest to go over to actually get a better idea of what different research teams have been doing on this thing. The last thing is I want to mention is that these models are still biased. So there are works in literature that show that like there are problematic and stereotypical association of images and text done by these models. And you can, for example, see these in the OpenAI CLIP paper, in which they somehow probe the model for different kind of attributes and show that like the model has learned bias from the data. And this is somehow expected since they got data directly from the web, probably without super hard check. Even public dataset like the Lion dataset contains some stereotypical dataset. It's hard to tell people not to use these models. I think it's relevant that we are all aware that like these models have problems, and when we somehow use this in, for example, production, it's important to check some of these issues and see if we can somehow reduce the bias in our models in production. So quick notebook and demo time, I guess. Now let me move this. So I prepare a couple of line of code here. So this is my clip wrapper. So what I'm gonna show you is that we can create embeddings with Fashion Clip, and we can use these to do some kind of search. So for example, this is what I'm using here is the Kaggle dataset. So it's a dataset of I think it's 10,000 images, not much more, I guess. So it's not very informative, but it's small enough that I can run it on Colab and do some minor experiments. So what I can show is that I have a function that takes clip image encoder and generates an embedding. So I'm generating the embedding for the image number 10 that is this image. So let me do this. Whoop. So the shape of this object is 1,512, where 512 is the dimension of the embedding of used by clip. So let me remove this and just show a couple of, these are the dimension inside the embedding. Oh yeah, forgot this. So this is the dimension inside the embedding. What we can do, for example, now is to create a text embedding. For example, get text embedding of, for example, this is a black shirt and a red shirt. These are text embeddings, and again, the shape should be 2 by 512 exactly. Now what we can do is that we can do zero-shot classification. So we want to see if we can classify this correctly as a black shirt. I mean, it's a black with yellow lines, but this is definitely more of a black shirt than a red shirt. So what we do is that from shippy.speed shelter distance, I'm gonna import cosine function to compute the similarity between these. So 1 minus cosine of image. This is the first image and the first text. And we're gonna do the same thing for the second text. And as you can see, the similarity between a black shirt, that is text 0, is higher the similarity between the image and the red shirt, that is text 1. So this shows like a bit of classification. You can also like do this for just color classification. And I guess you can also do short sleeves versus long sleeves. I did not try this. I hope this works. Yeah, it works perfectly. So the idea is that this is a short sleeve kind of shirt, and this is and obviously it's not a long sleeve. So the first score is higher. Look at how simple it is once you have like the model trained to generate the embeddings and start doing this kind of classification, in which you can just get like these big catalog of image, and you can just pre-annotate it with a bunch of different factors. So I have the embeddings already computed for the entire data set. So let me see how many images I have here. Let me just check that like these are normalized. Okay, so what I've just done is that I've previously computed the embeddings for all the 10,000 images in the dataset, so we don't lose time loading the dataset itself. But what we can do now is that we can try to do some text retrieval. So how text retrieval works in this way is that we get the embeddings of, for example, a green shirt that, as we said, text embeddings.shape. Mistyped again. Shape. It's 1 times, it's 1 5 12, and we compute the similarity between all the text between the text embeddings of interest, that is a green shirt, and all the image embeddings. So what text image scores is gonna hold is the similarity between our caption of interest, a green shirt, and all the images that are as follows. So what are we gonna do is that we are gonna get the most similar image ID, that is the argument with the maximum value. So it's the ID of the highest score, and its image with ID 8716. And we show the image, and it's indeed a green shirt. If we want to do a red shirt, we can do the same here, and it should be a red shirt, an elegant shoe, for example. I mean, we can see these in better in the team, I guess. And we get an elegant shoe. So we can actually search the vector space for image of interest, but we can also do zero-shot classification. So let me try to green shirt again. And this is our green shirt. So let's take the green shirt again, and let's try to do zero-shot classification of a bunch of like kind of labels, for example, colors, sleeves, kind of thing. So these should be colors, and if we look at the representation, we see that like green is the one with the highest color. So I am applying a softmax to just get to a probability distribution, but it is that green has the highest score. Instead, if we do sleeves, you should have like short sleeves, or at least is expected. And yes, this item has like a highest probability of being short sleeves than long sleeve. So this is idea of like how you can do things with just the embedding space. Now I have the demo that like it might be more interesting to look at. So one thing we can look at is, for example, shoes. So these are shoes. We can do shoes for women, for example. Sorry, let's start again. These are shoes for women. We can do elegant shoes for women, for example. We can do elegant shoes for men. And we get elegant shoes for men, but we can also do sport shoes for men. And again, here we are searching on a embedding data set of like 20,000 images, and look at how precise the model is in finding like images that match. For example, you can have a blue shirt. You can have a red shirt. Maybe I want a red shirt with long sleeves. Maybe I want a red shirt with long sleeve just for women. And you see like all these items tend to be pretty good prediction. Or I want a red shirt or long sleeve for men. You can also search for like red jumper. But yeah, you get the idea, I guess, behind this. And the big value, I think, behind this is that it offers the possibility of doing this kind of task in a manner that does not require annotation. You can easily fine-tune your model using standard scripts that are online. The loss itself is very easy to interpret, and it's very easy to explore the space, even if you are not like kind of a a core ML person, because it's just like having things that are close together, and having like image that don't matter far away. Another thing I can quickly show is like the classification part, if this works. For example, here we have Nike dress. So again, this is the classification, and we have Adidas dress, Black Knight dress, and Nike tank top as classification labels, and the model correctly tells that this is a Black Nike dress. We can also add another label that can be, I don't know, a cute puppy. That doesn't make any sense, but I guess that again, the model is gonna predict black Nike dress. Yeah, I think that's it from my side. I'm happy like to answer any question regarding like what we have done and like which are like the things we did, or like if you have any question, I'm happy to answer that. Okay, maybe close this, I guess.
Yeah, that was really interesting. Thank you, Federico. So yeah, you have a lot of questions.
Okay.
So we'll go through them. So we'll start right at the start. So from Abhinav, he asks, do you also create native samples during training?
No, that's a very good question. So no, negative sample can actually increase a lot the performance, and also like reduce training. Currently, no, because like it's not super easy to find negative sample for both the text side and the image side for the fashion domain. One thing we could have done was like search for in batch difficult image to classify, but that also requires a lot of computational power, because every time you need to recompute the similarities between all the images, so it's not super efficient. But no, that is a great suggestion, and like if you have computational power to do this, negative sample is like a very good solution to apply to these kind of things.
Cool, thank you. So another one from Hitesh. So he just wants a bit of clarification. So he understands that text and images have different embeddings, but the same dimension and in the same vector space. And he wants to know if training using contrastive loss helps both of those vector spaces align.
Yes, that is the idea. And also like if you, I didn't mention this, but actually if you look at the loss of clip, you see that when you reconstruct the similarity matrix, the loss of that the OpenAI folks have implemented, but also like comes from a paper of like a couple of years ago on medical imaging, is a contrastive loss that look at the classification score both row-wise on the actually image, on the actually image versus all the caption, but also like column-wise, that is caption against all the images. So yes, that is the idea of like somehow the contrastive loss.
Oh, thank you. So one from Joydeep. So I'm trying to normalize two vector spaces, one for voice and the other for speech to text, both using the same voice, into one embedding space, run a neural network for sentiment classification. Will dot product work in this use case as demonstrated by you? Isn't dot product a scalar number, and where is the normalization?
Sorry, can you, I'm not sure I understood the process, like which is.
Yeah, so he has two items or two vector spaces. One is for voice and the other for speech to text. He's trying to put those both in the same embedding space, and then or both put both of them into the same vector maybe, to run a neural net over those for sentiment classification. Oh, okay. So I think he's asking how should he put those two vectors together? How should he put the voice vector and the speech to text vector into the same vector space? Would you suggest using dot product, or should you normalize?
So if I understood correctly, there are two modalities, and both information have to be used to do prediction for sentiment. Is this like the task?
I think so.
I'm not sure if like the task requires this kind of contrastive alignment. Like if you already have the data and you want to do sentiment classification and you have like sentiment annotations, you can train the model to do this kind of classification. If instead your task is like to compute somehow the similarity between the two different modalities you have, that's where I think the dot product can indeed be helpful. I'm not sure if for a future sentiment classification task this can be useful, but I'm not like very knowledgeable of like speech data, so I might be like getting this wrong.
Yeah, no worries. Okay, thank you. So another one from Abhinav. He wants to know if he wants to retrieve images from a query using Clip and partly using a sparse retriever on captions from a database, like using BM25, is there a way for ranking the retrieved images in order for which one is better? So I think trying to merge both the dense vectors and the sparse vectors and ordering them in some way.
That depends a lot, I think, on the specific domain. There are domains in which I think like sparse retrievers still work very good. What I think that like the dense retriever like Clip is able to capture is properties like colors, for example, that are often not mentioned. So the thing is that like I think the best thing is like maybe to combine the scores with a weight, so that you can somehow get the best of both worlds, but it's hard to say without looking against at the actual data. But you can definitely like take the scores, normalize them, and then create a combined score to order all your resulting images. They definitely look at different things, I guess. The Clip retriever is gonna look at the properties of the images, while BM25 is gonna look at like description in the text. So the best way to combine these depends a lot on the data itself, I guess.
Cool, interesting. Thank you. So one from, we only have a couple of minutes left, so try and go through them quickly. From Amit, he wants to know if you faced any overfitting issues while fine-tuning both the encoder weight released by OpenAI. What learning rate did you use, and did you use any data augmentation?
Yes, so the answer is yes. It's not only overfitting, but it's also like catastrophic forgetting that is an issue. And we used like the learning rate, it was like 1 at the exponential -5. And the things that I suggest, that people tend to suggest now, is that if you have a good image encoder, such as the vision transformer from Clip, you should freeze that and just train the text encoder. This was introduced by the lead paper. That is one of, it's called Lockheed Image Tuning, I think the title of the paper. But in this paper, they show that like if you lock the image tower, a good image tower, you can just fine tune the text encoder and get the result. For data augmentation, no. And the answer is the difficulty of data augmentation in this context is that we don't know what happens. Like we had like very standard images, and we didn't want like to have some issue, for example, with positional elements. So if you applied, for example, horizontal somehow flipping, you completely destroy the concept of left and right in Clip. So it's always kind of hard to understand which kind of augmentation to use. You can definitely use perspective augmentation, but we didn't use augmentation in this context. We already have like data to do this, I guess.
Okay, cool. It's interesting. Thank you. So if we have enough time for one more question, that would be great. And then the rest of them we'll try and get around to them after the talk, if possible. So quickly from Vasilis, how did you deal with potentially duplicate data, and how does duplicate data affect a model?
So I don't have an answer to this question because the data was cleaned by people at Farfetch. So I'm not sure which is the process they actually use to clean the actual data. I think duplicated data is not super bad if it's not too much, but I don't have a real answer to this.
Okay. Thank you, Federico. That was a really interesting talk, and there are a ton of questions. So I think you definitely captured a lot of interest there. So yeah, thanks again. It was really interesting.
Thank you
And
so much for
for everyone
inviting me.
else, thank you for joining. It's a great talk.
Thank you.
Thank you. Bye.